this afternoon is Philip Wesolek, who will talk about conjugacy classes in locally compact subgroups of S&P.
Thank you, and I'd like to thank the organizers for inviting me to this great workshop. Okay, so yes, conjugacy classes in locally compact subgroups of S infinity. So let's recall the definition. So S infinity is a collection of permutations of the naturals. What's interesting about this? Well, it's a totally disconnected Polish group under the topology of pointwise convergence. And the automorphism group of any countable first-order structure is isomorphic to some closed subgroup of S infinity. Conversely, every closed subgroup of S infinity is the automorphism group of some countable first-order structure in a countable language. Indeed, something a bit stronger is true. There are automorphism groups of some Frise limit in a countable language. And so this is sort of maybe the connection to homogeneous structures. So there's plenty of locally compact subgroups in S infinity, which don't always get a lot of attention in descriptive set theory. But what can we say about them? So there's an old fact that any totally disconnected locally compact Polish group, right, in fact group, has a basis at one of compact open subgroups. Having this basis tells us that every T.d.l.c, that's how I'll abbreviate this, Polish group is indeed a locally compact subgroup of S infinity. So S infinity, in fact, encompasses every T.d.l.c Polish group. And so, yes, the converse certainly holds as well. If you're a locally compact subgroup of S infinity, then you're a T.d.l.c Polish group. So maybe we should spend some time thinking about what these things look like. So it turns out there's many T.d.l.c Polish groups in mathematics. So for instance, the automorphism group of a locally finite connected graph is naturally a T.d.l.c group. And the way to see this is that the distance is first order definable. So a stabilizer of a point has a finite orbit over any other point. And so these things are interesting, or people in geometric group theory are very interested in these sort of things. Second countable profinite groups, for example, the countable power of Z mod 3Z is another example of a T.d.l.c Polish group. More interesting still is locally compact second countable p-adic Lie groups. For example, GLN-QP is again a T.d.l.c group. And lastly, of course, countable discrete groups. And for the model theorists in the audience, if I just give you a Polish group or a closed subgroup of S infinity, how do I know the automorphism group is locally compact? So there's an easy exercise to see that if you have a countable L structure, then the automorphism group is locally compact if and only if there's some finite collection of elements such that the group theoretic algebraic closure is equal to the whole thing. And group theoretic, right, is the collection of elements of M that have a finite orbit under the pointwise stabilizer of these guys in the automorphism group. Okay. So one thing you might ask is that we have these T.d.l.c Polish groups all live inside of S infinity, and sort of there's a lot of tools to analyze Polish groups inside S infinity. So one thing you might ask are, can we prove some general theorems for such groups? And probably not if we include discrete groups. So discrete groups are sort of full of terrible examples. So naively, we could ask, what about if we exclude discrete groups and we just look at non-discrete T.d.l.c Polish groups? And for a long time, people thought that, well, no, this should be just as all the badness of discrete groups probably shows up in here. But turns out that was wrong. So surprisingly, the answer appears to be yes, is that having a non-discrete T.d.l.c Polish topology really gives you non-trivial structure. And so, for example, Willis had a paper in the mid-90s that really got people thinking about this, and then results of Kopras, Reed later on. So what's the moral? So the moral is that non-discrete T.d.l.c Polish groups, i.e. non-discrete locally compact subgroups of S infinity, are interesting mathematical objects which appear to admit interesting general theorems. And furthermore, their study may be approached by a monotheoretic and descriptive set theoretic methods, which is good because I'm a student of descriptive set theory. Okay, so what might you ask about these things? And so since we're talking about homogeneous structures, many automorphism groups of homogeneous structures, or if you prefer closed subgroups of S infinity, admit a co-meagre conjugacy class. So for example, the following admit a co-meagre conjugacy class. S infinity was long known to do that. The order automorphisms of the rational order have a co-meagre conjugacy class by some work of Truss, although I've been told that this had been maybe known earlier. And then the automorphism group of the random graph also admits a co-meagre conjugacy class. And so, okay, so maybe I should remind you, a co-meagre set in a Polish space contains a dense G delta. So it's dense, but it's also very dense. It sort of fills up the whole space. And the observation that was made was that none of these examples are locally compact. And so this led Kekers and Rosendahl to ask, can a non-trivial T.d.l.c. Polish group admit a co-meagre conjugacy class? And some remarks, so indeed, they ask if a non-trivial locally compact Polish group can admit a co-meagre conjugacy class. And however, connected locally compact groups cannot even have a dense conjugacy class, and this is by an unpublished result of Hoffman. And so the question reduces to what I have written here. And I should remark that the above question indeed asks about the non-discrete T.d.l.c. Polish groups, because no discrete T.d.l.c. Polish group can admit an even a dense class. Okay, so in the course of this talk, I hope to sketch the proof of the following theorem. A non-discrete T.d.l.c. Polish group does not admit a co-meagre conjugacy class. And this is sort of an example of this structure that you get from a non-trivial T.d.l.c. Polish topology. And this is, I guess, a contribution to this idea that there are general theorems that can be proved about such things. Okay, so we should also, so the way that this proof will go is I'll recall some preliminaries about locally compact groups for you. Then we will look at T.d.l.c. Polish groups with a non-meagre class, prove some theorems there, then look at the dense T.d.l.c. groups with a dense class, and prove a positive result there from which the theorem is a corollary. So preliminaries, locally compact groups have a left invariant non-zero outer radon measure, which is unique up to positive multiples. So the example is Lebesgue measure on the additive group of real numbers. And the key here is that it's left invariant, and the other thing is that it's the radon measure, which means it can be approximated from the inside by compact and from the outside by open. So it's a very nice measure. And I'll recall to you this theorem one more time, is that a T.d.l.c. Polish group has a basis at one of compact open subgroups. And this, so we should remark that these compact open subgroups are not necessarily normal. So there's, in fact, there's plenty of non-discrete T.d.l.c. Polish groups which are simple. For example, there's an old theorem of Titz that says that there's an index 2 simple subgroup inside of the automorphism group of a regular tree. And these subgroups are profinite. And this is sort of what really gets at why a non-trivial topology is important and has strong structural ramifications, is because profinite groups are actually quite well behaved. And we will exploit this to prove the theorem. That's the next slide. So these subgroups will be the abstraction to a co-meagre conjugacy class. Okay, so I should recall the definition. A profinite group is an inverse limit of a surjective inverse system of finite groups, so whatever that means. So the examples to keep in mind are something like the countable power of Z mod 3Z, or less trivially, the inverse limit of Z mod PNZ, and that's just sending 1 to 1 for all these cyclic groups. This is your binding maps. This is sometimes called the p-adic integers. So the thing that we'll use quite frequently is that profinite groups have a basis at one of open normal subgroups which have finite index. And profinite groups behave like finite groups. And this is really the key. If you have your favorite theorem about finite groups, chances are there's some profinite analog. And this is really what we need to, the key step into proving the main theorem that we're setting about to prove is using this intuition. Okay, so now let's consider T.d.l.c. Polish groups with a non-meagre class. So we need a few preliminaries. So first, let's take some topological group and H some element of it. So I'll use this lowercase, this subscript O to indicate that K is an open subgroup. H sup U will denote the conjugacy class of H and U. And C sub U of H is just the set of elements which commute with H. And this is the centralizer of H and U. And the fact, so this goes back to this, what's your favorite theorem about finite group theory? And this is the one that we'll end up using. So if F is a finite group, and you have some element of it, then the conjugacy class of H and F is in bijection with F mod the centralizer. And the point here, which we'll make heavy use of, is that the order of the size of the conjugacy class is exactly the index of the centralizer. Okay, so the goal now is to think, I want to come up with a version of this for profinite groups. But when I'm in a profinite group, cardinality is not the right way to measure things. We want to use the Haar measure. So can we get a version of this result where now you're looking at Haar measure over here? It turns out you can. And that's the following key lemma. So let U be a profinite group, and let's consider the Haar measure to be normalized. So when you're a compact group, your Haar measure is finite. And suppose we have some element with a non-null conjugacy class. So then for all open normal subgroups, the size of the centralizer in the quotient, right, this quotient's finite because this is open, is bounded by 1 over the measure of the conjugacy class. And the size of the centralizer in your big profinite group U of H is bounded by 1 over the measure of your conjugacy class. And so this isn't quite what this is. It's similar to what happened in the finite case, but it's a little bit different, right? Because it's not, you have some fuzziness around what's going on. And in fact, this doesn't have to be equal. This can be strictly smaller. So there's an example due to John Wilson, which shows that. Oh, so what's the proof? Okay, so take some open normal subgroup. So now take a transversal, HK1, HK1 inverse, so on, for the conjugacy class of the coset Hn in the finite quotient U mod n. So certainly the conjugacy class of H and U is contained in this collection of cosets. So further, by the monotonicity of the measure, you get that the measure of this conjugacy class is bounded by the measure of this collection of cosets. So by the invariance of the Haar measure, you know that the measure of this conjugacy class is less than or equal to the size of the conjugacy class of the coset Hn in U mod n times by the measure of n. But now U mod n is a finite group, and so we can apply this theorem that we know, or theorem is this sort of obvious fact. So the size of this conjugacy class in U mod n is just exactly the index of the centralizer. So writing this out, we get that the measure of n times the index of the centralizer. We can write this as the size of this finite quotient over the order of the centralizer in U mod n of coset Hn. But this is 1, and that's because we chose it to be normalized. So the measure of the conjugacy class of H and U is bounded by 1 over the size of the centralizer in this finite quotient U mod n. So rearranging, we get that the size of the centralizer is bounded by the size of the centralizer in U mod n, coset Hn. It's bounded by 1 over the measure of U, and we have 1. And now it follows that, in fact, the size of the centralizer in U of H is bounded by, of H in U, is bounded by the same amount, because if you give me n elements, I can find some small enough or some large enough finite quotient that witnesses them being distinct. And so we have 2. Okay, so using this, we get a nice characterization, a nice equivalence of measuring category for conjugacy classes. So the conjugacy class of H and U is I guess I should say what this is. U is a second countable profinite group, and H is some element of U. Then the following are equivalent. The conjugacy class of H and U is non-meagre. The conjugacy class of H and U is open. The measure of the conjugacy class is greater than 0, where mu is normalized Haar measure. And of course, you don't need normalized here. It's just convenient. And finally, 4, we get a completely algebraic characterization. There is some integer, if you prefer, such that the order of the centralizer of coset Hn in U mod n is less than or equal to m for any choice of open normal subgroup n. And so what's the proof? Well, 1 implies 2 is just a bare category. 2 implies 3 is properties of Haar measure. 3 implies 4 follows by the key lemma. And 4 implies 1 is essentially running the key lemma proof backwards. It's not so hard. But you might say, well, are there actually interesting examples of this, right? Finite groups are profinite. And so therefore, and so since it's discrete, certainly any conjugacy class is open, right? So maybe that's it, but it turns out no, there's plenty of non-discrete examples. So Rosendahl has a clever example that there is a non-discrete second countable profinite group with a non-meagre class. And indeed, once you know this example and this theorem, you can build a whole family of these things. Sort of not, really it just comes from having a fixed point free action on a finite group. Take an automorphism group of a finite group that acts fixed point freely. Okay, so now in order to address our goal, where we want to prove the non-existence of a co-meagre conjugacy class in a T.d.l.c. Polish group, we need to get this for all T.d.l.c. Polish groups, not just profinite ones. And so to do that, we need a lemma. So in a T.d.l.c. Polish group, an element is periodic if it is an element of a compact open subgroup. So lemma 1, let G be a T.d.l.c. Polish group and H some element. If the conjugacy class of H is non-null and H is periodic, then H is torsion, and the conjugacy class of H in W is open for any W, a compact open subgroup containing H. And what's the proof? So fix some compact open subgroup containing H. It's sort of easy to see that the conjugacy class of H in W is non-null with respect to G's Haar measure. By uniqueness of Haar measure, the conjugacy class of H in W is non-null in W. By the previous theorem, the conjugacy class of H in W is open and H is torsion. So from this, we get a nice corollary. Suppose G is T.d.l.c. Polish group and H in G is periodic. Then the following are equivalent. So 1, conjugacy class of H in G is open, conjugacy class of H in G is non-meagre, and the conjugacy class of H in G is non-null. And so the proof isn't so hard. So 1 implies 2 is just bare category. 2 implies 3 follows from the fact that properties of Haar measure and the fact that G is a case sigma. So this is a classical result that a T.d.l.c. Polish group is a case sigma. And 3 implies 1 is the previous lemma. Okay, so now we're ready to think about groups with a dense class. So the theorem we prove here is if G is a non-trivial T.d.l.c. Polish group and you have some dense conjugacy class, then that class is both meager and null. And you might say, well, do we actually have such things? And it turns out we do. There is, by a clever example due to Aiken, Glasser, and Weiss, there's a non-trivial T.d.l.c. Polish group with a dense conjugacy class. Okay, so what's the proof? So suppose we have some element in G such that the conjugacy class of H in G is dense and non-null or non-meagre. Now, since it's dense, it means it must fall into some compact open subgroup at some point and therefore is periodic. By the equivalence of category measure for conjugacy classes, the conjugacy class of H and G is open. Lemma 1 now implies that H is torsion. So since this conjugacy class is dense and every element has the same order, it implies that G has exponent order of H. So that meaning that every element has order which divides order of H. So every compact open subgroup of U is torsion, but turns out there's a rich body of work on torsion profinite groups. And so applying 2 deep theorems by Wilson and Zelmenov on torsion profinite groups, you arrive quite quickly at a contradiction. So in fact, this was the special case that I proved, and then it ended up being the general case. And the corollary is a non-trivial T.d.l.c. Polish group does not admit a co-meagre or co-null conjugacy class. So some remarks. So the theorems of Wilson and Zelmenov are in fact quite deep results. So Wilson's theorem relies on the classification of finite simple groups. We may avoid using them in the special case of ample generics, which if I have time, maybe I'll sketch out if people are interested. So the ample generics case is actually an elementary proof, which follows from the key lemma. So once you have that key lemma on the finiteness of centralizers, it's easy to rule out ample generics. And of course, ample generics means you have a co-meagre diagonal class on G, the n Cartesian power of G for all n. The category measure equivalence for conjugacy classes in profinite groups seems independently interesting. And on the next slide, I have a question which is related to this, which seems like it might, this equivalence may well shed some light on, or maybe the technique of proof. And this result, as I mentioned, supports the suspicion that a non-trivial T.d.l.c. group topology imposes non-trivial structure. and some questions. So is there a model theoretic proof? And this, I've been told, is probably too hopeful, but what about in the case of ample generics? Since we have an elementary proof there, there really is no, I'm not using classification of finite simple groups or something there. Rosenthal's example is solvable. So must all second countable profinite groups with an open conjugacy class be virtually solvable? And so you need the virtually bit here to rule out finite groups, right? You can just take a finite simple group and that has this property. So, and I can prove this in a couple special cases, and it runs into some interesting deep problems in, I guess, asymptotic finite group theory, like what happens to derive length if you have properties on a sequence of solvable subgroups. Something that I came across, and this is what I mentioned about this equivalence of measure and category possibly being applicable or give insight into other problems, is this. Is for you a profinite group, put T sub n the collection of elements in U that have order n. So if this thing has positive measure, is it non-meagre? And you'll note that this thing is conjugacy invariant. So I've thought about it a little bit, but I haven't spent that much time. But it seems like you may be able to use that same argument, something about you're reducing to the finite quotients and trying to bound the size of this set in the finite quotients. And this actually has some deep ramifications in profinite group theory because positive measure doesn't really tell you much, but non-meagre says that you actually have a coset in there. And having a coset that all of whose elements are torsion actually can give you some tools to prove theorems about finite groups. So. And then what about other pathological behavior? So in my process of learning about this, I came across people in geometric group theory and abstract harmonic analysis asking about other pathological behavior, in particular the following. So is there a non-discrete T.d.l.c. Polish group which is topologically finitely generated? It means it has a dense, finitely generated subgroup. Topologically simple has no proper, non-trivial closed normal subgroups, and is generically periodic, meaning that it has a dense set of elements, all of which the monothetic group they generate is compact. So the automorphism group of the random graph has these properties, but of course is not locally compact. And Tarski monsters have these properties, but are discrete. So it's, again, this kind of question is, where do locally compact groups fall? Do you having non-trivial profinite groups lurking forbid something like this? And in a slightly different, this was asked in a paper of Willis in a slightly different manner, but this is sort of the version for people who know things about the automorphism group of the random graph. Okay, and this is the proof for ample generics, but I'll stop there. Thank you.
Solvable. And do you have some other reason to believe it's
So
for the fact that this one is
no, so there's so conjectures in finite group theory. So what you can reduce it to is you can reduce it to an element. So you can reduce it to finite groups that have an automorphism that has a small fixed set. So that's the elements other than the identity that are fixed under the action by the automorphism. And there's some conjectures, long-standing conjectures in finite group theory, that you have to bound the derived length of those things. And if those were known, then this would automatically be true, or this would be an easy consequence. And in fact, there are some special cases in which they know bounds on the derived length, or on the derived length they know it if you say your automorphism has prime order. So in special cases, I can prove this virtually solvable. Oh yeah, I have my notes. So the paper is these notes here I have, and I have with me, and I can show you what I have.
yeah, but my question is regarding
the whole proof is on the archive. Yeah, it's on the archive.
So it's on the archive?
Yeah, you're welcome.